Hi everyone, this is a lesson on the trapezoidal rule in calculus and numerical integration. You've probably learned by now about Riemann sums and using rectangular approximations for areas under a curve. And you've probably learned how to evaluate antiderivatives and definite integrals and perhaps use substitution, general power rule for integration. And there are a lot of functions out there for which some of those methods don't work. And yet maybe we want a better approximation achieved through numerical methods than that given by a rectangular approximation, like a left endpoint approximation or a right endpoint or midpoint approximation. So the two functions of integrals that you see here are examples of ones that you really could not easily do by hand at this point in your calculus career. And maybe we would have to resort to numerical approximations and try to find out, what's the best way we can achieve some kind of approximation of these definite integrals. So because we can't really use those algebraic methods really provided to us by the fundamental theorem of calculus, we have to find other ways. So as we just mentioned, those other ways, we could do a left endpoint approximation, right endpoint, or a midpoint approximation. And of course they all use rectangles, sometimes of varying widths, but they all to some degree use of rectangles. That's kind of the bottom line. So you probably learned when you did rectangles, either inscribed or circumscribed, around the curve, or maybe some kind of combination of the two, as is the case with midpoint approximation, there was often a lot of positive error or negative error. So the whole idea behind the trapezoidal rule that we're going to explore today is, instead of using rectangles to approximate the area under the curve, and remember that's given to us by a definite integral, we can use trapezoids. Really because they allow for less empty space, that negative error that you would have learned about, than using inscribed rectangles, and also a more accurate approximation that we would often see with an over approximation with circumscribed rectangles that you learned as the positive error. So to give you a good visual of what this looks like, this is our standard kind of diagram for this. So we have a continuous function f of x on a closed interval from a to b, and if you look at, tilt your head sideways, that's where the trapezoids come from. The vertical lines that you're looking at that go up to the curve, they basically are the bases of the trapezoid. That's why you got to turn your head to the side and look at this sideways. So the one end of the trapezoid is obviously straight. That falls right along the horizontal, the x-axis, and it's the other end over by the curve, that side of the trapezoid, where, it's the slanted edge of the trapezoid. Now notice in this case the trapezoids are all of equal width, and we're going to refer to that width as delta x. And the way in which we can find how wide each of our trapezoids are is by b minus a over n. So a and b are the endpoints of the interval, and n is the number of subintervals. Just like you would be told that when you did rectangular approximations, you'll be given that same information here. So what we're going to do is pretty much derive where this trapezoidal rule comes from in calculus and what the formula is going to be that you'll be making use of. So let's start with how you get from geometry area of a trapezoid. So we all know that area of a trapezoid to be given to us by 1/2 the height times the sum of the bases, b1 plus b2. All right, so what we're going to be doing is basically applying this formula to the picture on the previous slide and coming up with how this formula, the trapezoidal rule, is going to look to give us an approximation of area under a curve. So we're going to go one trapezoid at a time. So let's kind of slip back here, and we'll start over on the far left. All right, and we're just going to apply the basic formula for trapezoid. Okay, so we have 1/2. Now the height, that's going to be your delta x. All right, because remember the height, you have to turn your head on the side. So your height is basically this right here. That's your height, which is given to us by delta x. All right, so far we have 1/2, the height that is delta x, and then we need the sum of the bases. So we need kind of f of x sub 0, because that's going to be this height here. All right, so that would be f of x sub 0, and this other one here, right, that's like base 2, so that would be f of x sub 1. All right, so let's go ahead and start writing this up. So first trapezoid, we have 1/2, the height, and times the sum of the bases. So that's going to be f of x sub 0 plus f of x sub 1. All right, so that's just our first trapezoid. All right, next trapezoid. All right, so no, we need 1/2 the height. All right, again, now your height is this one here. The sum of the bases. Now notice that the one side, the one base, is shared with that first trapezoid, and then we have the other one here. So maybe we'll call this like x sub 2. All right, just for argument here. So the first height, base 1, is going to be f of x sub 1, and the second one's f of x sub 2. All right, so let's go back. So second one, it's going to be 1/2 the height and the sum of the bases. So f of x sub 1 plus f of x sub 2. All right, let's do another one. All right, so the third one, so here's your height. Okay, that's your delta x. Let's maybe call this one x sub 3, just to kind of make it easier to notate everything. Once again, you'll notice that one of the sides is shared with the previous trapezoid. So the one base is going to be f of x sub 2, and the other one's going to be f of x sub 3. So 1/2 the base times base 1, or the height rather, is delta x. So then we have f of x sub 2 plus f of x sub 3. Okay, so of course we would keep going on and on and on. If you take a look at the pattern that's developing, all right, let's see if we can kind of come up with a general statement. All right, so basically it's going to be 1/2 delta x. I think everybody's got that part. And then we're going to have, you know, depending upon how many subdivisions we have, notice how this last one here is x sub n. Well, that would be your final one. So notice how each of these subscripts, it's, you know, consecutive integers, basically, you know, whole numbers. All right, so we could notate this very easily as f of x sub n minus 1 plus f of x sub n. Now that looks awfully messy, and no, you're not going to do that because we're going to summarize this. All right, so take a look at this long expression we have. All right, you'll notice that the 1/2 delta x is common to all of them. So we could think of this, you know, the 1/2 delta x. Think of that as maybe being, let's factor that out. All right, so we have 1/2 delta x. All right, now take a look at what remains. We have an f of x sub 0. We have an f of x sub 1, and that's doubled. All right, notice how it repeats because it's there and there. F of x sub 2 repeats there and there. If we had kept going, f of x sub 3 would repeat. The only ones that show up only once are the very first one and the very last one. Everything else repeats because if you go back to your picture, they share a side, a wall. Right? These are all held in common between two different trapezoids. Okay, so how that translates then into the formula, we'll have 1/2 delta x and then f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2. And we would keep going along those lines until we get to the very, very, very last one. And that's only going to show up once. All right, so the big thing to remember is everything in the middle is always doubled. And that is the trapezoidal rule. All right, and what you'll be able to do is basically use that sum of the areas of the trapezoids to come up with an approximation for the definite integral, the area under a curve, from a to b of some function f of x. Notice it is an approximation. As you've probably learned, that is important. So the official statement of the theorem, what it looks like, is that, which you'll notice is really just what we did. Notice how in the front, the 1/2 delta x is re-expressed as b minus a over 2n. You can think of it either way. All right, everybody kind of has their own way they like to remember it, but notice how the rest is all the same as what we just talked about. There is the IntMaths program on your graphing calculator. We'll work through that with one of our examples, so you might want to have your calculator handy. So I have a few different problems for us to try, and hopefully you'll see that it's pretty easy to work with. All right, so the first one we're going to do is the trapezoidal rule to approximate the area from 0 to pi of sine of x dx. Of course, that is one you could do by hand. So it would be interesting to compare the answer we get using the trapezoidal rule with what it really should be if you evaluated that definite integral according to the fundamental theorem of calculus. All right, so one thing you could do, it's up to you, if you want to figure out delta x, like the height of your rectangles, you could do that first if you want. Right, remember delta x is always going to be b minus a over n. N is going to be 4 in this case, so we just have pi over 4. So that's how wide each of our trapezoids is. All right, so remember it's an approximation, so it's going to be approximately equal to, remember in the front, we have 1/2 delta x, so we have 1/2 times pi over 4. Or if you preferred it just to do it there as the b minus a over 2n, that's fine. So we're going to write it all out and set it all up. I'll be showing you some shortcuts you can do for the function evaluation on your calculator. All right, so we're going to start at f sub 0. All right, and as we talked about, the first and the last items only show up once. All right, now this is where you have to do a little mental math. Because in this case you're starting at 0 and you know that your trapezoids have to be pi over 4 wide. So you basically just start adding on pi over 4 to 0. Alright, so the next one, remember, gets doubled because this wall of the trapezoid is going to be shared by the first trapezoid and the second. So it's going to be 2 times f of pi over 4 plus, now add on pi over 4 again. You get pi over 2, because it would be 2 pi over 4. Add on pi over 4 again, you get 3 pi over 4. And then add it on again, we end up at the end at pi. And remember, that shows up only once. Alright, so in the front, that's going to be pi over 8. Alright, so what we're going to do is basically allow the calculator to do all that evaluation of the function values, really do it for us. The reason why it's good to do that is because it eliminates and minimizes really some of the rounding error if you were to kind of do it on your own and just jot down what the decimals were. So it does lead to as good of an approximation as you're going to be able to get. Alright, so let's go to the graphing calculator. Under y equals, we're going to put the integrand, sine of x. Alright, you might want to take a peek, make sure you're in radian mode, which I am. Alright, and what we're going to do is make use of that function notation that hopefully you've seen, that y1 that kind of mimics your f of x notation. Alright, so we're basically going to type it in exactly as we hand wrote it out. So we're going to start with y1, because since our function is under y1, we'll do y1 at 0. So that's where it's mimicking your f of x notation. Alright, plus 2 times, and now we need the function value of pi over 4. Time sign is optional. I just get paranoid, so that's why I include it, but you don't need the actual time sign there. Alright, so that's 2 times the function at pi over 4, plus, and now we need 2 times the function at pi over 2. Plus 2 times the function value at 3 pi over 4. And then finally the last one is just the function value at pi. Alright, so that's everything we just wrote out. Hit enter, and hopefully everybody got that. Now remember, you need to multiply that still by pi over 8. We haven't done that part, so this is not your final answer. So times pi over 8. And 1.896 would be our approximation of this integral by using the trapezoidal rule. Alright, so let me go back and just kind of jot all that down. Alright, so let me show you some, the trapezoidal rule that you have in your IntMaths program on your calculator. Let me just clear that out. If you go ahead and run the IntMaths program, I'm sure you remember this from before. So A was 0, B would be pi. We had 4 subintervals. And remember, the IntMaths program, it's going to give you the left, right, and midpoint rectangular approximations. You'll notice the little wormy thing in the upper right corner of your calculator screen still going. So hit enter, and there is the trapezoidal approximation. And pretty darn close to what we got when we did it ourselves. What the calculator's doing is actually finding the mean, the average of the left and right endpoint approximations. So it will be pretty close. What we did is probably a little bit more accurate. So we would definitely want to go with that. All right. Now the other thing that would be interesting is, let's see if we actually, evaluated that definite integral. Pretty sure this is one you've seen before. I forgot a parenthesis. Here we go. All right, because remember with the trapezoidal rule, we got approximately 1.896. All right, that's really what it should be. So it is a little bit off. Of course, it's only an approximation. Just like you had seen with rectangles, had we done more trapezoids, so increased our n value, that definitely would have given us a better approximation that is closer to this actual real answer. All right, let's try another one. So this time we're doing 5 subdivisions. The integral 0 to 1 of the square root of 1 minus x cubed. All right, so we could figure out our delta x first if you want. Remember, that's b minus a over n. So that's just going to be a fifth. So that becomes what we're going to add on. So our integral so we have 1/2 delta x so now we start in. So we begin with f of 0. Remember, that's only once. Now we start adding on a fifth. So we'll have 2 times f of 1/5 plus 2 times f of 2/5 plus 2 times f of 3/5 plus 2 times f of 4/5. And then finally, the last one, remember, only appears once. That's going to be 5/5, which brings us to 1. So multiplying the fractions in the front, we have a tenth, so we'll multiply by that at the end. We can go ahead and do that whole part in the square brackets there. We can do that on our calculators once again. So let's go back under y equals. We'll change out the function. And we'll get started. All right, so we have f of 0 plus 2 times f of a fifth. So if you want to do decimals, if that's easier, feel free. Plus 2 times the function value at 2/5. So that's 3/5 plus 2 times the function value at 4/5. And then finally the last one only shows once. And that would be 5/5, which is 1. Alright, so make sure that's what you got. So we still have to multiply this by a tenth. So our final answer is 0.809. Now again, just out of curiosity, we could go ahead and, what is the exact answer supposed to be? I'll just do y1 since I already have it under there. See how close it came. Nah, so-so. All right, so let me go back to write all this up. So for the part that we had done on the calculator, that had given us 8.095. So when we multiplied that by a tenth, we had about 0.809. All right, one more. All right, so now we're doing 6 subintervals. And so we're going from 0 to 2. So our delta x, b minus a, that's going to be 2 over 6, so 1/3. So our integral ½ delta x. All right, so we're starting at 0. So we got f of 0 plus, and now we start adding on a third. So we have 2 times f of a third plus 2 times f of 2/3. Add on another third. Now we are at 3/3, so that's 1. Then we have 4/3. Uh, 5/3. And finally, the last one is 6/3, which is 2. That puts us at the end. All right, so that's the part you'll want to do in your calculator. I guess you'll have to be using the decimals, or rather the fractions for those as you enter them, since the decimals won't round nicely. So multiplying the fractions in the front, we have a 6. So I'll give you a second to go ahead and try that on your calculator. I think you have the hang of it by now. Double check, make sure you're coming out with 0.695 for that part. And then of course you'll multiply that by 1/6, so our answer in the end is 0.116. All right, so a couple other side notes to discuss as we're talking about these numerical methods for approximating area under a curve. Let's kind of compare and think about the trapezoidal approximation as opposed to the midpoint maybe approximation, the midpoint one specifically. All right, so how they compare to each other in terms of, which is going to be maybe bigger than the real integral, like if we actually did Math 9 and evaluated the actual definite integral. Between the trapezoidal approximation and the midpoint approximation, can you come to some kind of generalization about how do you know which one is going to be bigger than the real answer or less than the real answer? And it really comes down to the concavity of the curve you're talking about. All right, so if you have, for instance, a function that's concave down, all right, think about what that looks like. Let's see if I can draw it up here. All right, so maybe it kind of looks like this. Okay, I'm going that way with my concavity. So a trapezoidal approximation, remember, that's going to have us drawing trapezoids, all right? And the way in which, it sort of starts out looking like a rectangle. All right, but then the top is slanted, and that's where the trapezoid comes from. All right, so like that might be our first trapezoid. Here comes our next one. Again, the sides pretty much look like a rectangle, but then the top is sloped. All right, if you think about if we kept drawing this, hopefully it becomes apparent to you that the trapezoidal approximation for the area under the curve is always going to be less than what that area actually should be. All right, the reason is because it's concave down. Notice you have a little teeny tiny bit of negative error in there. All right, so if you know the curve is concave down, the trapezoidal approximation is going to be less than the real answer for the area under the curve. All right, now let's think about the midpoint approximation. I'll do that in a different color. We can even think, because that is a rectangular approximation. And remember the way that is, all right, pretty much the sides start out as, rectangles. But then remember it's the midpoint of the top of the rectangle that's hitting the curve. All right, so notice there what we have. We have a little bit of positive error, this little teeny tiny bit jutting out right there. Got a little bit of negative error there. If we did this again, all right, well, here's the top, all right, because here's the sides. All right, that's going to kind of look like this. If we did another one, all right, so here's the midpoint. It would be looking like that, all right? You do end up with some positive error. That's going to cause a midpoint approximation, if the curve is concave down, to be bigger than the real integral answer for the area under the curve. All right, now let's think about what happens if the curve is concave up. All right, so maybe it looks like this. All right, and we're going to pretty much go through the same thing. So we'll start with trapezoids. So the trapezoids, remember, they start out looking like rectangles. So here's your slanted, like right there. Maybe this is, yeah, this one actually looks like it's a little wee bit above. All right, because if you're starting at that left endpoint, notice how the slanted side of the trapezoid, it's going to lie just a hair above where the curve actually is. Right, now see that one, how it was just a little bit teeny tiny above. So what ends up happening is that a trapezoidal approximation ends up being just a little bit bigger than the real integral answer for the area under the curve. All right, now a midpoint approximation. All right, so maybe this is the sides right here. Maybe here's our first rectangle. Remember, it's the midpoint that's going to be at the top. So maybe it looks like that. Second one, right, here's the sides for the second one. Here's the midpoint. Here's the third one. I think you can easily tell. Notice this big negative error on that first one. That's actually what ends up driving. And you can see you have a little bit more negative error here. A midpoint approximation then ends up being less than the real integral answer. All right, so just kind of some interesting side notes about how the concavity of the curve itself can even affect the goodness, if you want to think of it that way, of a trapezoidal approximation versus a midpoint approximation, both in comparison to the real answer of the definite integral. And that brings us then to a mention of the last of the numerical methods, called Simpson's rule. This is named for the British mathematician Thomas Simpson, 1710 to 1761, lived only a short 51 years. It's considered, really one of the last numerical methods. And what it does is, of all the numerical methods, though, it is the most accurate of all of them. When you compare the Simpson's rule answers to the left endpoint, right endpoint, midpoint, or trapezoidal rule. So there definitely is a hierarchy in terms of how good these answers are. Left, right, and midpoint are all kind of in the same category. Trapezoidal rule is going to give you a better answer than those three, but then Simpson's rule is going to give you a better answer than all of them. Simpson's rule is not something you are responsible for knowing how to calculate by hand, according to the College Board syllabus for the AP examination. But it does bear mentioning. So what Simpson's rule looks like, if you think about how we did the trapezoidal rule, the sides were pretty much rectangles, but then the top was slanted, so when you looked at it on the side, that's where your trapezoid came from. Well, imagine now that the tops are actually segments of curves. They're parabolic segments. So you can see the dotted lines here, and that's really what we're talking about. This is a picture out of an old calculus book. It's probably one of the best pictures I've found as to what Simpson's rule looks like. All right, again, you're not responsible. The textbook, if you take a peek in there, I'm sure you'll see how to hand calculate this, and you'll probably be happy you don't need to know how to do it. But it is possible. You know, it's just a little bit more tedious than trapezoidal rule was. The trapezoidal rule does tend to show up on the free response on the AP exam, as do the other rectangular approximations. Simpson's rule, I always like to make mention of it. It is the last of the ones if you go back to that int_meths program. Let's see, maybe we can just run it on this one. Yeah, let's just use this function. If we went ahead and ran the int_meths program, let's see, which one was this? This was, might as well do the real thing. 0 to 1. This had 5 intervals. All right, so there's your left, right, and midpoint. There's the trapezoidal rule. This is, we had gotten for, this was number 2 that we looked at. The answer we got was 0.809, so you can see that's darn close. But take a look at the last one. That is your Simpson's rule. Again, it's considered to be the most accurate of all of the numerical methods. So that Simpson's rule is like 0.8368. Let's see what it would be if we evaluated the definite integral. I think we had done this, but I forget what we got. All right, so 8368 is what we got through Simpson's rule. All right, that's definitely closer than we were with the trapezoidal approximation to the actual answer for the definite integral. All right, so Simpson's rule, you know, so you know about it and have heard about it, it is considered the most accurate of the numerical methods. But thank you for watching and spending this time with me. Hope this makes sense and will be of help to you.